this lecture, I'll be discussing mixed integer decisions. Mixed integer programming refers to problems containing both integer and continuous variables. It means that some decision variables are continuous and can take on fractional values, and other decision variables are integer, can take on just integer numbers, 1, 2, 3, and so on. One example can be site selection and resource allocation. For resource allocation, we usually deal with continuous variables. But for site selection, we are dealing with a binary situation or integer numbers. We either choose a side or we don't. Now here, we want to formulate a mixed integer problem and solve it in Python. Here's the problem statement. A contractor, Susan, has to haul gravel to 3 building sites. She can purchase as much as 18 tons at a gravel pit in the north of the city and 14 tons at one in the south. She needs 10, 5, and 10 tons at site 1, 2, and 3 respectively. The purchase price per ton at each gravel pit and the hauling cost per ton are given in the following table. So these are the input parameters that we need for our model. There are 2 pits, 3 sites, and we have the cost for each pair of pit and sites. Susan now needs to hire the truck and their drivers to do the hauling. Each truck can only be used to haul gravel from a single pit to a single site. In addition to the hauling and gravel cost, there is a fixed cost of $150 associated with hiring each truck. So that's the integer part. So we can hire 2, 3, or 1 truck drivers. So that's integer. A truck can haul 5 tons, but it's not required to go full. So that's the capacity limit for each truck. For each combination of pit and site, there are now 2 decisions to be made: the number of trucks to be used and the amount of gravel to be hauled. The amount of gravel is a continuous number. Fractional values are acceptable, 5.5 tons, for instance. But the number of trucks, always integer number, 0, 1, 2, or 3. So here we define 2 decision variables. One x sub ij, which represent the number of trucks hauling from pit I to site j. So indices are pit and sites. And the other decision variable is y sub ij, referring to the number of tons of gravel hauled from pit I to site j. So xij are integers, but yij can be continuous. And here we have 2 indices. One, I, which represent the pit, so north and south. The other one is j, representing sites. So we always use list to model indices. So one list for I, and there are 2 items in that list, north and south. One list for j or sites, and there are 3 elements in that list, 1, 2, and 3. So the objective function is obviously minimizing the cost. So the cost information is given here. So we have 2 pieces of information in this table. One, hauling cost. The other one is a price per ton. So we can add up these 2 numbers. For instance, the total cost from North Pit to site 1 is 300 plus 100. So this number plus this number. And the hauling cost from south side to site 1 is this number plus this number, and the same for other. And these are the coefficients you see here. So this one is 300 plus 100. This one is 300 plus 190. So that shows the cost between each pair of pit and sites. We also have a fixed cost, 150 for hiring drivers. So a fixed cost of $150 associated with hiring each truck or driver. So this $150 is the fixed cost, so we can take it off, and then we have the X sub ij depending on the number of trucks that we are going to assign between each pair of pit and side. Then we have that fixed cost. The first two constraints are capacity limits for our pits, the north side and the south side. This constraint is the capacity limit for each truck, because each truck can haul 5 tons. So Y sub ij, which represents the number of tons hauled from pit I to site J, should be less than 5 times the number of trucks. So if we have one truck, then it should be less than 5 tons, because each truck can only haul 5 tons. And the rest are demands for each site. So we need to deliver 10 tons to the first site, 5 tons to the second site, and 10 tons to the third site. So that's the mixed integer model for this example. As you can see here, decision variables are both integer and continuous. We have 2 indices, pits and sites. And now we want to solve the model using Python and Groby. First, we need to define lists and dictionaries and input parameters. The first one is pits. So I define P as a list, and there are 2 items, north and south. The other index or list is sites. So I define S equal to site 1, site 2, and site 3. And you can define or assign other names to each element. Then we have the hauling cost. So I define a dictionary. That dictionary has a 2-element key for each value. So from north pit to site 1, the value is 400. From north pit to site 2, the value is 490. From north pit to site 3, the cost is 460. Now from south pit to site 1, the cost is 600. From south pit to site 2, cost is 530. And the last one, from south pit to site 3, the cost is 560. The other input parameter is maximum capacity for each pit. So maximum capacity. So I define a variable named pit max, which is a dictionary. The key is north and south. So value for the north pit is 18 tons, and for south pit is 14. These are the maximum capacity. The other parameter is price per ton. So We define a variable named price. For the north side is, for the north pit is 300. The south pit is 420. We also have some hauling requirement or demand for each side. So I define a variable named hauling, which is a dictionary. So we assign a value for each side. S1 needs at least 10 tons. S2 needs 5 tons. And S3, the third side, needs 10 tons. We also have a fixed cost for hiring truck. So we define a variable hiring cost. It's equal to $150. Now let me run it. Okay. Now we can create the model. So first we import GrowBPy from GrowBPy, import all functions. Then we create the model object using the model statement with capital M. We call it MIP, Mixed Integer Programming Example. Then we need to define decision variables. Here we have two decision variables, X and Y. Decision variables are dictionaries. X, number of trucks, add some comments for us. Number of trucks hauling from pit I to site J. And Y is another decision variable presenting the amount of gravel hauled from pit I to site J. Both X and Y have two indices. It means that we can write two for loops for I in pits and for J in sites. Xij is equal to, we call the model, then we add variable. X is the number of trucks, so the v type or the variable type is integer. growb.integer. Lower bound is 0. Upper bound is infinity. So growb infinity. The same for the other decision variable for I in pits. For J and sites, Y ij is equal to model dot add variable. This time the v type is continuous. Lower bound is 0. upper bound is infinity. Let's run it. Okay. This is a minimization problem. So we call model dot model sense, which is a reserve word. It's equal to Groby minimize. If it was maximization, we just change minimize to maximize. We need to update the model, so model dot update. Now we can define constraints. One constraint is about maximum capacity for each pit, so we can write a for loop for I in pits. Model dot add constraints Yij is a decision variable. Now let's look at the formulation that we have here. So it's this summation. So y sub n1 plus y sub n2. So we are going to use a quick sum. That quick sum is a summation over sites. So for each pit, we have a summation over site. So when we want to implement this, we need to pay attention to indices here. So quick sum for j in sites, so it's a summation over sites. It should be less than or equal to pit max value for each pit. So if you look at here, we had a variable which was a dictionary representing maximum capacity for each pit. So pit max I refers to that variable, and I is the key for that dictionary. So we get access to each key and then we extract their value. So we took care of the first two constraints. The other constraint is the third one, maximum capacity for each truck. That you can see it's defined for I over pits and j over sites. So we follow the same format. So we are going to have a nested for loop for I in pits, for j in sites, model dot add constraint. So you don't see any summation here, so we don't use quick sum. We have y sub ij, yij less than or equal to 5 times xij. So this was the third constraint here. The other constraint is it's defined for each side, and you can see it's the summation over pits. So we can write a for loop to take care of these three constraints. The for loop is for I in sites. So for each side, we add a constraint, model dot add constraint. you will see the summation of two terms. So we have a quick sum function, quick sum. So it's the summation over pits. So quick sum y ij for I in pits should be equal to Halling J. So here we define the demand or Halling requirement and variable, which is a dictionary. So for each site, there is a minimum requirement, and that Halling variable is referring to that variable. So here we are using I for pits, then we use J for sites. We need to distinguish them. Okay, let's make sure that we don't have any typo here. Okay. It seems that we are done with defining all constraints. Now we can update the model. So model.update. So these constraints are assigned. Let's run it. Syntax error. Okay, when we see this error, it means that the pair of north and S1 is not defined. So first we check our decision variables. Okay, so you can see here, I defined two variables after for loop, xij, but when I was defining the variable, there was a typo. Now it's xi and I. That's why it doesn't recognize the pair of north pit and first side. So let me change this. The same for this variable. It should be y, I, and j. And let's run it, the decision variables. And let me see if it fixes. Okay, here we go. So when we define I and j, we should have the same indices for defining variables. So the mistake was here when we were defining the decision variables. We had x, I, and I, but it should be I and j. Okay. Now we can define the objective function. As you can see, for objective function, we have two terms. The first one is cost related to variable yij. The other one is the fixed cost related to variable xij. So we follow the same format. So we define objective equal to, for the first term, we use the quick sum. We have coefficients, Halling cost, which is a dictionary with a two item key. So we have I and j. Times y, I and j. And it's a summation over both I and j. So we'll see two for loops for I in pits and for j in sites. Okay. So Halling cost is referring to this dictionary over here. And the key has two elements. The first one is pit, the second one is site. That's what you see here. So Halling cost, I and j, and then we get access to their value times the decision variable. It's the capital Y, and it's the summation over I and j. Then we have the second term, the fixed cost, 150 times the summation of x variables. So we will use another quick sum. We we have the hiring cost, which is a number times xij for I in pits and for j in sites. So it's the summation over both I and j. So you see two for loops inside the quick sum function. Hiring cost refers to this value, 150. Okay. Let me run it. Now we need to assign this objective function to the model. Model.set objective. Then we pass the objective variable. Okay. Now we have all elements for the model, decision variables, constraints, and the objective function. Now we can just optimize the model. Okay. We have the optimal solution based objective function. Now we want to print the result. So we check the model status. If model.status is equal to Groby optimal, print optimal value for our objective function. We call the model.objval. And now we want to show the optimal solutions for x and y. So we have two indices. We can write two for loops for I in pits, for j in sites. Print this statement. So from pit I to site j, send this amount yij dot x, and that's how you extract the value for each y and y sub ij. This amount times with this many truck, which is xij dot x. I make it integer, so it just drop the decimal points. Okay, let's run it. So here's the result. The optimal value shows the minimum cost, and then you have the result. From pit N to site 1, send 10 tons with 2 trucks. From pit N to site 2, send 0 tons with 0 truck. There is no truck, so you cannot send any, you cannot haul gravel. And from pit N to site 3, send this amount, 8.00 tons with 2 trucks. Nothing is assigned from pit S to site 1, but from pit S to site 2, 5 tons with 1 truck, and that's the result you communicate with the decision makers, and that's what they understand. So this is the best solution, and that's the best course of action that we can propose based on the result of the optimization model. Okay, now this example was relatively small. So when we were defining input parameters in lists and dictionaries, we could do it manually. However, remember, we learned how we can populate lists and dictionaries by reading data from Excel or text files. So for large-scale optimization model, we can use the append method and those techniques we discussed before to automate this process, to read data from text file or Excel sheets, and then define the variables or the input parameters we need for our optimization model. So with this example, I wrap up our discussion about mixed integer models.